Measuring the Cosmos, a Cosmic Yardstick, written by Neil deGrasse Tyson. Have you ever looked up at the night sky and felt a sense of awe and wonder? Stars scattered across the vast expanse, distant galaxies swirling with light, and planets tracing their paths through the cosmos. The universe is a place of incredible distances and mind-boggling sizes. To make sense of this immensity, astronomers use a special set of measuring tools, the astronomical system of units. Imagine trying to measure the distance between cities in inches. It would be a very cumbersome and impractical task. Similarly, using our everyday units of measurement, like meters or miles, to describe the vast distances between stars and galaxies would result in incredibly large and unwieldy numbers. The astronomical system of units simplifies these measurements, making it easier for astronomers to study and understand the universe. This system provides a convenient and standardized way to express the enormous distances, masses, and timescales involved in astronomy. Just as we use different tools to measure different things in our daily lives, astronomers rely on these specialized units to navigate the cosmos and unravel its mysteries. The cosmic clock, ticking in days. Time, the relentless river, flows differently in the vast expanse of space. But even in the cosmic ballet, we need a reliable beat to keep track of celestial movements. Astronomers, in their quest to map the heavens, have chosen a familiar unit of time: the day. But this is no ordinary day confined to our planet's rotation. The astronomical day is defined as 86,400 seconds, precisely calibrated to atomic clocks, ensuring accuracy across the cosmos. Why the day, you ask? Well, astronomy is all about observing celestial events. The dance of stars across the night sky, the phases of the moon, the orbits of planets around the sun. These events are all measured in terms of days. A single rotation of Earth on its axis relative to the distant stars marks one complete day. This cosmic clock allows astronomers to track the movements of celestial objects with incredible precision. Think of it as the rhythm section of the universe, setting the tempo for the cosmic symphony. Weighing the universe, the solar mass. Now let's talk about weight, or more accurately, mass, the amount of matter an object contains. In the cosmic realm, we encounter objects of unimaginable mass: stars, galaxies, and black holes. Trying to express their mass in kilograms or pounds would be like trying to empty the ocean with a teaspoon. Enter the solar mass, the mass of our very own sun, approximately 1.989 times 10 to the power of 30 kilograms. That's a 1 followed by 30 zeros. Instead of juggling these mind-boggling numbers, astronomers use the solar mass as a convenient unit to describe the mass of other stars, galaxies, and celestial objects. For instance, a star with a mass of 2 solar masses is twice as massive as our sun, while a galaxy with a mass of 100 billion solar masses contains the mass of 100 billion suns. This unit of measurement provides a relatable benchmark for understanding the immense scale of celestial objects. It's a way of saying, this star is a heavyweight, tipping the scales at 10 times the mass of our sun. One small step for man, one giant leap for astronomy, the astronomical unit. The distance between Earth and the Sun, averaging 93 million miles, is known as the astronomical unit, or AU. The AU is a fundamental unit in astronomy, providing a baseline for measuring distances across the solar system. Mars orbits the Sun at an average distance of 1.52 AU. Jupiter lies at an average distance of 5.2 AU, while Pluto resides roughly 39.5 AU from the Sun. Using the AU, we can visualize the relative distances within our solar system. Catching a ride on a light beam, the light year. Venturing beyond our solar system, we encounter vast distances. To measure these, astronomers use the light year. A light year measures distance, not time. It's the distance light travels in 1 year. Light travels at about 186,282 miles per second. In a year, it covers about 5.88 trillion miles. Proxima Centauri is 4.24 light years away. The light we see from it left over 4 years ago. Parallax and parsecs, a stellar surveyor's tool. Imagine standing on Earth and observing a nearby star. As our planet orbits the Sun, our perspective of the star changes slightly. This apparent shift in the star's position, relative to more distant background stars, is called parallax. It's similar to how an object appears to move when you view it from different positions with one eye closed. Astronomers use this parallax effect to measure the distances to nearby stars. The smaller the parallax angle, the farther away the star. To express these distances, astronomers use a unit called the parsec, which stands for parallax of 1 arcsecond. 1 parsec is equivalent to about 3.26 light-years. So a star with a parallax of 0.1 arcseconds would be located 10 parsecs away, or about 32.6 light-years from Earth. The parsec is particularly useful for measuring distances to stars within our own galaxy, the Milky Way, and to nearby galaxies. It's a tool that allows astronomers to create a three-dimensional map of our cosmic neighborhood. Visualizing the vastness, putting units to work. Let's take a moment to appreciate the incredible scale these units represent. Imagine shrinking our sun, a star with a diameter of about 865,000 miles, or 1.39 million kilometers, down to the size of a grapefruit. On this scale, Earth would be a tiny dot, smaller than a grain of sand, orbiting about 50 feet away. The nearest star, Proxima Centauri, would be another grapefruit located a staggering 2,500 miles away, roughly the distance between Los Angeles and New York City. And the Milky Way galaxy, our cosmic home, would span a mind-boggling 100 million miles across, about the same distance as a round trip to the sun. These units not only help astronomers make sense of the universe's vastness, but also allow us to grasp the sheer scale of the cosmos. They transform abstract numbers into tangible concepts, allowing us to visualize the immensity of space and our place within it. The astronomical system of units is more than just a set of convenient measuring tools. It's a language that allows astronomers to communicate and collaborate across countries and continents. Just as scientists around the world use the same units for mass, length, and time in other fields, astronomers rely on these standardized units to share their discoveries and build a collective understanding of the universe. These units also play a crucial role in testing and refining our theories about the cosmos. By precisely measuring the distances, masses, and movements of celestial objects, astronomers can test the predictions of Einstein's theory of general relativity, study the evolution of stars and galaxies, and even search for signs of life beyond Earth. The astronomical system of units provides a framework for making sense of the universe's grand design. It allows us to unravel the mysteries of black holes, probe the early universe, and explore the possibility of life on other planets. The development of the astronomical system of units was a gradual process, driven by the need for more precise and standardized measurements in astronomy. Early astronomers relied on Earth-based units, such as the stadium, a unit of length used in ancient Greece, and the solar day, the time it takes for the sun to return to its highest point in the sky. However, as astronomical observations became more sophisticated, the limitations of these Earth-centric units became apparent. The development of the telescope in the 17th century revolutionized astronomy, allowing astronomers to observe celestial objects in unprecedented detail. With these advancements came the need for more accurate and standardized units of measurement, tailored specifically to the vast distances and timescales of the cosmos. The astronomical system of units continues to evolve as astronomers develop new technologies and make ever more precise measurements. For instance, the development of radio astronomy in the 20th century led to the discovery of pulsars, rapidly rotating neutron stars that emit beams of radio waves. To measure the incredibly precise timing of these pulses, astronomers needed even more accurate units of time. This led to the adoption of atomic time, based on the vibrations of atoms, as the standard for astronomical timekeeping. As our understanding of the universe deepens and our technological capabilities advance, we can expect the astronomical system of units to continue to adapt and evolve, providing us with the tools we need to explore the cosmos and unravel its many mysteries. The journey of exploration and discovery is far from over. Each new observation, every measurement refined, brings us closer to comprehending the intricate workings of the cosmos. The astronomical system of units is more than just a collection of units. It is the language of astronomy. It allows us to translate the universe's grandeur into numbers we can comprehend. It allows us to speak of light years with the same ease we discuss miles, to compare the masses of stars as we do apples and oranges. So the next time you gaze upon the night sky, remember the astronomical system of units. These units are not merely tools for scientists, but a testament to human curiosity, our relentless drive to explore, understand, and find our place in the grand cosmic narrative.